Hey there, we're about to do Codeforces Round 724. This is a Div 2. And from the score distribution, it looked like the end of this round was relatively easy, but I guess we'll see. How can you add something to make it nice? Oh, at least once. Oh, I remember. Okay. Present B at least once. Oh, well, you know what exactly you have to add. Okay, that's what you do. So you just repeatedly add. Oh, it's like, if there's a negative number, you have a problem. Otherwise, you just make 0 through 100, something like that. Yeah, I don't like my solution anymore. Should I realize that? All right, let's just make it. 1300 milliseconds. It's like 300 cubed, and then you, no, 300 squared, and then you sort them. That should be fine, I think. I don't know why it takes so long. Anyway, let's just do some more problems. Every prefix max. Okay. It's just how many prefixes have the same ratio, right? No, not zero. And then outright in. E. Oh, I see. I mean, you could say like 1-3, yeah. So we're just gonna run through everything. And okay. s dot find just give a string that. S dot find string always strings dot swap mesh. Alright, D and E got solved. I am grid of so it can be 00011. Yeah, okay. This is kind of crazy. Oh wow. So everybody has a path to 0. So someone has like a 6, 5, 4, 3, 2. Wait, how do you do this? Martin's pretty fast. Yeah, 2000 by here. Okay, there has to be some really efficient solution. Here's linear. This one could be at most a 2. I'll do D because I don't know how to do this. Why 61 3 no? Like you have a 6, you have a 1, and that's 1, you have a 2. Yeah, it has to be like the closest number to it has to be the last number, something like that. I see, I see. Okay, so that's not too bad. I can do T then. These. I think it's true. And then otherwise you repurpose. So read the whole input. And then otherwise B will insert B and this was V. I guess we don't need a multi-set, but whatever. It didn't give this yes. 1, 1, 3. Oh. Okay, it's fine, I think. As long as it's the most adjacent in either direction, should be fine. It is not a good time. Not sure how to do E. This guy is at most 2. It can only be 2 if this is 1, this is 1, this is at least 1. At least strictly larger than at least 1. Is it just, are we just figuring out how many of these we fill out as 0? 126. Ah, that is what we're doing. As long as there's at least 1 0, then you're okay. Great. This is still case template. We want it. And what's the deal here? Okay. If the entire thing is this. This is zero. Recent minus not int 2.q, and then if q.n and y. Okay, and one more problem. He's got 100 points in me. Is A or B? same letters. I think for 3 the answer is 12. Oh, that's not what I want. I guess I want 1, the answer is 2, I guess. For 3 the answer is 12. For 4 you got A. So P doesn't lose. But also if you got A and B, then you can have an A here. So there's a lot of, this fish has a lot of rocks. So let's start with 8 times, and then if you go B here, stop. 1 plus, if we go B here, then they can go B here or here, either way you finish. There's 2 things you can do, plus 2 things they can do. And the only other thing to do is go A in the middle. See when. I think it's 56. Yeah, so you get to either, there's 2 n's, so it's an n minus 1, 0 basically. You can, it's a 0, if it's 0 you can split into 0, 0, or you can split into 1. It's 1, you just, I guess I should figure out who wins each of those. So for t, and you can get to tk plus from 0 n, you can get to 0k and 0n minus 1 minus k, or you can get to 1k, 1, and you can get to 0k and 1 minus 1 minus k. And in all these cases, in this case, this isn't actually missing. So, yeah, you can't do A that close. You can't, yeah, you can actually. 1, you can have a credit 0, 0. For B, you can put it in. This is just 1. You put in A, B, you put in A. So you can't put in right here. You can't put in right here. Alright, an experiment. Let's do some of this. But then how do we path? That's kind of crazy. Alright, let's just try this. So that's not great. There you go. Great, so yeah. Seems zero pushback. SG K0 XOR SG minus 1. Which is always true. And now if it's at least 1, then we can do this one. It's just 1 0 1 0 1 0. I'm not sure. Yeah, I can't do anything, so I can. If I do that, it's just like this. What's wrong with this statement? That's really weird. Okay, it's always 1 0. So yeah, basically you do first one, and then it's stay with 1. You don't want to do that. You have to do this. Oh, wait a second. Return A, and then so you give them a 0 and there's 1. This is what you need to achieve the 1 by getting to 0. How do you get to 0? Extra 1. That's so one way you can get 1 extra 1. Another way is you can give 0 extra 0. You can do anything. Right, you can just play this any way possible. Are you serious? It doesn't matter how you play this. So, some sort of Catalan type of thing.
Okay, so let's try this then. No, no, yes, yeah. 2 times n times dp n minus 1, 0. What's wrong with this? Oh. Is this what it is? It's still getting 0 for 3. Why is that? Oh, what is going on? So oh, if it's a losing state, we need to add 1. Just do 0, 1, lose 0 also. Let's freeze. It's possible that I just got this wrong. Let's just run over the case then. Two, two. If we go B here, it's tough. A here. It's 2 options. So isn't that right? Why isn't it? seems to be true. You can just play the game however you want. Wait, no, this is not the right way. It should not. No, this is not right. Oh, it's not just times. Oh, what is it? Oh, that is so weird. It's not times. Times is not correct at all. Yeah, times is not correct at all. No, so you're splitting it into two games, and those games can just interleave however you want. You just go until there's no moves possible. And how does that happen? Because how do you end up with? What is it for? What is a finish board? Finish board looks like. Yeah, anything that's not played is because there's A and a B next to it. So you pick empty spots. There can't be two empty spots. Yeah, pick empty spots with gaps. The number of empty spots has to be equivalent to n mod 2. Okay. And then out of those choices, you get like a factorial. Yeah, we get a factorial. So not the first one. First one's not going to be empty. If n-1 spots, we choose E empty. But every time we choose an empty, there are essentially, so it's actually n-1 minus empty, choose an empty. So if empty goes 4, not possible. So n minus empty. What equals 3? That would be 8 minus 3, choose 3. So 5 choose 3, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, that's correct. Okay, so n minus e choose e. And then I guess that's factor n minus empty. N minus 1 minus empty. I failed. And 4 is just 1. Okay, I guess that's fine. Okay, and F is now worth 1940. So 67, 67. And F decays. How many points does F decay? I guess it decays 10 points per minute. So well, okay, I guess he's still got about 10 minutes to pass me. Mr. Maxine. This is also assuming my A holds up, which is not that clear. This is really slow. Maybe I'll just remove F4. So then I'll move F5. Oh, this is kind of annoying. And then move F6. Oh, can I do this? No, it doesn't make sense though when I put after it. Okay, that's cool. Great. Now let's look at A. How slow can this be? Alright, try to TLE it, and so what we're going to do is put one test case. Oh, that's why. Oh, that's nasty. You just have 50 of these. Okay, this is terrible. Wow. I guess I will hack myself afterward if I don't fail. This is such a no. All right. So, yeah, I'm just going to talk about my solutions to the problems. And, well, for A, we'll have to redo the solution. So, for problem A, basically you've got this process where an array is nice if for any two distinct elements of the array, the absolute value of bi minus bj appears in B at least once. And then all the elements of B must be distinct. So we want to add several integers to A to create a nice array of size at most 300. And if A is already nice, you don't have to add anything. And really the key observation here is if A has a negative number, then you can never add enough numbers to make it nice, because basically, let's say it contains negative 1 even. If you have negative 1, then let's think about the biggest number in A. Even if the biggest number in A is like 1,000, you'll still, based on your nice rule, you'll still need 1,000 minus negative 1 or 1,001 in the array. So no matter how far you go adding big elements, it will always basically demand one bigger. So anything with a negative number is a no. And that's why this one case is a no. Otherwise, if everything's at least 0, then what you can do is really easy. You just set up an array that contains all of the numbers between 0 and 100. And that way, that is definitely a superset of your array A, and it's also a nice array. So that's the idea. And I guess I need to go code that now. So we'll save that terrible version. And then I'm just gonna do this, I guess. Oh, I don't have to do that actually, I'll just do this. This is kind of nice. Yeah, so if A's min element is negative, it's 0, otherwise it's just yes. And what we're gonna do is I guess we don't even have to build this. We'll just print it. Yeah, so this looks good. Prints 0 through 9, 0 through 4, and 0 through 12, which is pretty much what we want. Yeah, so this is what I would do, and if I were rated, I might have to resubmit this, I don't know, but I'm just going to take a gamble at it as is. Let's see, can Maxime still pass me? So 1870 points for F. That's 1870. So he's got like 2 or 3 minutes left. Anyway, we'll keep going. So problem B, what is this? Oh, okay, the max of the string. So we want to find, basically we're given a string. We want to find the shortest string that doesn't appear in the string. And if there are ties, we want the lexicographically smallest string. So, you know, if both AC and BA don't appear, we would want AC. So this, it turns out, the actual solution is actually really easy because n is at most 1,000. What that means is that for sure there's some 3-character string that doesn't appear just by pigeonhole principle. It's not quite true for 2, unfortunately, but it is true for 3. And so, yeah, essentially, you just try all the strings. So I just build all the strings. First, I build all the 1-character strings in order, so A, B, C, D, and so on. Then I build all the 2-character strings, so AA, AB, AC, and so on, all the way to AZ, and then BA, BB, BC, and so on. And I use strings find method. And once I cannot find a string within S, I just return it. That's the answer. And so the runtime for this, it's I guess it's technically, no, it's basically like, it's basically n squared. I guess it's technically n squared times log base 26 of n, because log base 26 of n is the string size we can end up with. But either way, this is super fast and plenty good enough for this problem. So yeah, so the key idea in terms of implementation is just to find a nice way to kind of generate the list. All of the 1-character strings, and then all of the 2-character strings, and then all of the 3-character strings, and you want them to be in order as well. Yeah, you can use recursion, but you can also just make a list like this, and this is kind of a nice way because you can just expand it by 26 each time. Okay, so that's B. Let's look at C. Yeah, so C, we have this string of D's and K's, and we want to cut it up into different pieces, but every piece has to have the same ratio of D's and K's. So we want to know the maximum number of pieces we can cut it into while maintaining this ratio. And actually we want to solve this for every prefix of the string, not just the whole string. And n is quite large, n is up to 5e5. So in this case, yeah, it turns out basically, if you think about a prefix and you think about all the cuts, every cut has the same ratio. So what that means is that every prefix, so for example, let's think about this. Let's take an example string. And then there's some more stuff. So for this string, there's an equal number of D's and K's. And I missed one. There's an equal number of D's and K's overall. And so in this case, we could actually cut it like this with 4 pieces. So this piece has an equal number of KD and DK. And the key insight here is that in order for all these pieces to have the same ratio, that also means that all these prefixes have the same ratio. So this prefix, this prefix, this prefix, and this prefix. So really what we're doing is we're just counting for this prefix, how many smaller prefixes also have the same ratio as this prefix. And then that gives us a solution. Oh, I mean, it's way bigger. Okay, yeah. Basically, I have a map of frequencies for each ratio, and I just count the number of D's and K's that I've seen. One key thing that I do is, in order to normalize the ratio, I divide the ratio by the GCD. So that way 2 to 4 gets reduced to 1 to 2, 3 to 6 also gets reduced to 1 to 2. Everything gets kind of compressed to its canonical form. And then, yeah, the answer for this prefix is just the frequency of this ratio plus 1, because plus 1 for itself. And then that's the answer. So pretty simple solution. Just take some nice observations about these ratios and GCDs to speed it up. Check standings. Okay, looks like how many points is problem F worth now? 1820. So yeah, if it's only 1820 points, then nobody can catch me now. Yeah, I guess it's yet to be seen whether I fail A. Oh, this is not what I want to look at, actually. I want to see if anyone is hacking a successful. There is one. Okay, I guess we'll see. We'll see. All right, so now that we finished C, let's talk about D. Yeah, okay, this one I didn't do it too rigorously, but basically you've got an array A of odd length, and you're finding the medians of all of the odd prefixes. And you're given an array B, and you want to test the claim and see if B is actually generated from this process for some array A. Yeah, so essentially I worked out some different examples. Essentially the key observation is that every value in B has to be kind of close to the previous value. So for example, if we look at 6213, then the reason this is a no is because basically 6 is fine, 2 is fine, 1 is fine. But then once we add 3, 1 is not the closest value to it because there is a 2 in between. And so this is why this is a no. This is also a no for a similar reason. You have 4, -8, and then 5. So -8 is not the closest to 5. You have a 4 in between. But yeah, one tricky thing here is that this array is actually okay. So 1, 1, 1 is close to 1, 3 is close to 1. And then 1, even though there are other ones, this is actually fine because 3 is the next biggest thing after 1. So yeah, so basically, if you look at the code, I guess maybe a better way to implement this would be, no, it's a little tricky because you have to handle equal cases. But yeah, essentially, as long as the previous number is either equal to B, that's fine. If it's the biggest number smaller than B, that's fine. If it's the smallest number bigger than B, that's fine. So if it's one of the kind of closest numbers to B in the set that we've seen so far, then it's fine. And that's how I implement it. Yeah, and okay, so the reason is basically, if we look at, for example, the 6213. So 6213. So first, we know that the first element of A is a 6. And then we know there's 2 elements. One of them is a 2, and one of them is something else, or it might also be a 2. But because of the 6 being bigger, we know it's a 2, and we know it's something less equal to 2. And then for 1, we know we have a 1, and we know, I guess technically this could be 1, but let's just say we have the 1 here. And then again, because 1 is less than 2, we have a less than equal to 1 as well. And so then the problem comes in when we have a 3, because now we have too many numbers less than 3. The reason we have too many numbers less than 3 is that basically 1 is the median of this array, right? And in order for 3 to become the median, it has to be the number, like if you look at the array sorted, you have something 1, something, right? And we're trying to insert a 3, and we're trying to insert some other number. That means the 3 has to come right after the 1, and then something else has to be here too. And then the 3 becomes the median of the new array. Whereas if there's something in between the 1 and the 3, then we have a problem, because this becomes the median. And this is true in this case, which is, the problem is there's a 2, right? And that is exactly the problem here. This 2 is in the array, which prevents the 3 from becoming the median. And so that's why we essentially have this condition where we need the new number to be either equal to or just adjacent to the previous number in terms of the list of numbers we've seen so far. So that's the main idea there. Right, so that's D. Now I'll talk about E. Yeah, so E is kind of a tricky one. Basically, we have these two rules. We need to have numbers in a grid. And if you have any two adjacent cells that share a side, the absolute value of their difference is at most 1. And then if any number in a cell is strictly positive, larger than 0, it has to be strictly greater than a number in at least one of the cells adjacent to it. So if we think about these together, what does that really mean? Well, let's say we have a cell with a 7, then it has to be strictly greater than something next to it, right? But because of this rule, that thing next to it has to be a 6, right? And then we can apply the same logic to the 6. There has to be a 5 next to it. There has to be a 4 next to that, 3, 2, and so on. So there has to be a path, 7, 6, 5, 4, 3, 2, 1, 0. So essentially, any positive thing has a path to a 0. And the actual problem is we're given a bunch of, or a grid with a bunch of either zeros or these kind of hashtags or sharps. And we need to fill in these with any number. It can be 0, it can be positive, so that it's a valid setup for these rules. And we want to know how many ways we can fill it in to do that. Yeah, and so it turns out, this took me a bit of thinking, but basically it turns out once you decide where all of the zeros are, then, and you decide everything else is going to be positive, then everything else turns out to have its value decided for it. So this example is probably a little too big, but maybe we can do something like this for a small example. So let's say let's see. Let's just, I don't know, add one more 0. Okay, cool. And yeah, let's say we've decided these are all the zeros. Everything else is going to be positive. So for example, for this cell, well, we know it's positive, but we know it can't be 2 or bigger because it has to be, if it were 2 or bigger, it had to have a path bound to 0, 2, 1, 0, but that's not allowed. And really just the first rule, it has to be within 1 of its adjacent numbers. So basically we know, because of that first rule, we know that every number touching a 0 has to be a 1. Because they can't be bigger than that. And now then let's think about this cell, for example. Well, this cell is adjacent to 2 1s. So first of all, the only numbers we can put here are 1 or 2. We're not allowed to put 0 because we already decided it's not a 0 based on this first rule. And then if we put a 1 here, that's not good because it's not strictly bigger than anything next to it. So it has to be a 2. Same logic here. This has to be a 2. And so, yeah, same logic here. This has to be a 2. This has to be 2. And then this has to be 3. So you notice it actually turns into like a shortest path type of thing where every cell, the number of the cell becomes the shortest path from that cell to a 0. And yeah, basically the point is once you decide all the zeros, all of the positive numbers are uniquely determined. So there's only one way to fill out the board. So the answer is really just 2 to the power of the number of hashes. There is one corner case, which is that the grid has to have at least 1 0. If you have everything positive, you mess up this rule for the 1s, right? So that's why the answer for these two cases is 3 and not 4. But otherwise, it really is just 2 to the power of the number of these hashes. And so, yeah, the code is super simple. It's just counting the number of them to the power of that. And then if the entire board is hashes, so there's no zeros yet, we have to remove the one case where everything turns into a 0, into a positive. So nothing turns into a 0. And we subtract that case out, and then we have the answer. All right, and then problem F. Hang on, let me check this one more time. I see, so Maxime did solve F, and I have a less than 30-point lead So I guess if I had resubmitted A, I would also be in trouble anyway. Yeah, this is funny. We'll see if the A ends up failing system test or not. Okay, so for problem F, we've got this game on a circular board, and you can take turns placing either an A or a B on the board. You have to place your letter on an empty cell, and in addition, you cannot place the letter adjacent to a cell with the same letter. The player who has no valid moves left is the one who loses, and we want to compute the number of possible distinct games where both players are playing optimally. And you have to go until there are no valid moves left. So yeah, the first thing really to determine in this problem is what is playing optimally. Like what does that mean? What's the right strategy to play in this game? So for that, I ran an experiment, calculated some Sprague-Grundy values, and it turns out the values are super consistent. For every n, it's just 1 and 0. So essentially, there are two states in this problem. Oops. Oh, I'm opening up this box. Okay. There are two states in this problem. So for example, let's say n equals 6. Then we have 6 slots, right? And now let's say we pick somewhere and put an A. Well, we can just rotate all of these around because it's a circle. And even if we pick a B, it's the same. We could swap A and B. So let's just assume that we start by picking an A as the first vector. Then we end up with this segment where both sides are surrounded by A. So you can actually imagine it as a segment like this. And actually, I'll make n a little bigger. And then, maybe we'll pick somewhere here and we'll play B, right? And that corresponds to this. There's kind of an invisible A at the end here. Yeah, so what you'll notice is that these segments actually behave independently. And there's two types of segments. One segment is the kind of the same segment. And the other segment is the different segment, right? And those are the only two types of segments. And so that's what my states are here. So n0 means there are n stars. So this segment would be 4, 0, because there are 4 stars, or sorry, this would be 4, 1. This segment would be 6, 0, because there are 6 stars, and both sides are the same. And A or B, it's the same. Just make sure that both ends are the same. So yeah, again, this is 6, 0, and then 1 means that they're different. So that would be this, and then this would be, how many is that? 9, 9, 1. That is the state there. So yeah, so I computed the SG values for all these states. It turns out for every n starting from 1, the SG value of n0 is 1, and the SG value of n1 is 0. And in particular, what that actually means is, if you analyze this, is that it doesn't matter what the players do. No matter what choices they make, they're playing optimally. So you can just fill out the board any way you want until the game ends and there are no more valid moves. And both players played optimally, and actually the second player always wins. This is assuming n is at least 2. Like n from the original problem. Okay. Now, so now the problem is just counting how many ways we have to fill out the board until there are no more moves. And for that problem, it turns out there are basically only a couple different ways the board can be filled out. And it's based on which cells are empty. So I'll give an example. Okay, so first of all, you cannot have 2 empty cells next to each other, because in that case, there's always another thing you could fill in. For example, for this cell, because it only has one neighbor, which is an A, you can fill in a B. So in a final state, we can only have empty cells that are not next to other empty cells. And then the other thing, again, we're assuming we start with A. Now we're going to fill out we have to fill out a segment alternating fashion, A, B, A, B, A, because we cannot have two A's next to each other, or two B's. Then we'll have an empty cell, and then the other side of this has to be the opposite of this cell, or this letter. If it were an A, then we can actually fill this in with a B, so it's not finished, so it has to be B. So we'll have, you know, B, A, B, A, then we'll have another empty cell. Again, we have to do the opposite of this. Again, opposite of the last character. And then right. Okay. This is also fun. Yeah. Okay. So this is an example of an arrangement where this could be the final state. There are a bunch of empty cells, but they're all surrounded by AB, BA, AB. So there's something we can place here. So a key observation is that the number of empty cells has to be equal to n mod 2, because otherwise we get kind of messed up. For example, if this were missing, then we have this A adjacent to this A. So the number of empty cells, yeah, it has to be equal to n mod 2. And then now we just want to count. So now if we have the arrangement of empty cells, in particular if we had this, we actually know exactly how to fill it, because, well, again, we assumed the first thing was an A, so we know it's an A. Then we have to alternate A, B, A, B, A. Then again, we have to flip from the last character. So this A means we have to start with the B. Then we have to go A, B, A. And then we just fill it out. And then we can get everything exactly. So we're really just counting the number of arrangements like this, where the number of empty cells is equal mod 2 to n mod 2. And the first cell is not going to be empty based on what we decided. So we have n-1 slots, and we have E empty cells. And it turns out this is just a kind of a standard like stars and walls type of counting problem. The answer for the number of ways turns out to be n minus empty, choose empty. And that, yeah, that's the number of ways to pick E empty cells out of these n-1 blocks. So yeah, so I just loop up empty from n mod 2 up to at most n over 2. I guess this, I don't really have to do this, because if empty gets too big, then this will just be, for example, like 5 choose 7, something smaller, choose something bigger, it'll just be 0. But either way, it's fine. Make sure to jump by 2 so that you're always equal to n mod 2. This tells us the number of ways to pick those empty spots. And then there's one more key thing, which is for all these A's and B's, they can be filled in any order. So we have a factorial there. So we just need a factorial of the number of A's and B's that we're filling in. And so that's why we're multiplying by this. And then finally, we always multiply by 2n. The reason for that is that this is the choice we made at the beginning, which is that, hey, we're always going to start with the first character with an A. But in reality, we can start anywhere with either of the characters, so that's 2n choices. So we need to just multiply that out, and that's our solution. All right, so yeah, that's it for this contest for me. Again, I have my fixed A versus my bad A, but I'm not going to resubmit. I'm just going to take my chances, and we'll see in half an hour, or I guess maybe half an hour plus half an hour, or half an hour plus an hour, depending on how slow the systems are. I guess because A is the first one, we'll find out pretty quickly. So about half an hour. So we'll see if I pass. It'll just be like a fun little thing. I guess when this video comes out will be roughly when we find out. But yeah, that's all of the solutions for this contest. Yeah, thanks for tuning in. Feel free to like the video and subscribe if you want to see more videos from my channel, and I'll see you in the next one.